All right, we are in section 11.4 looking at more tests for convergence and divergence. So in this section we're going to look at the comparison tests. These comparison tests really are just what they sound like. We're going to be comparing series to other series. So the idea behind these comparison tests is to compare a given series with a series that is known to be convergent or divergent. Okay, so if we have a series that we already know converges, we can compare this one to it and see if it also converges. If we have a series we know diverges, we can compare our current one to it and see if it also diverges. So this is the comparison test. So suppose that the series A and B are series with positive terms. So if the series B is convergent and A is less than B for all n, then A is also convergent. And if series B is divergent and A is greater than or equal to B for all n, then A is also divergent. Okay, so think about it this way. If we know that, so B gives us some value and we know that it converges, okay, so the value is finite, well then we also know that if A is smaller than B and B is finite, then A is also going to be finite. Whereas if we have B is some series that diverges, so it has an infinitely large value, and we know A is bigger than B, then if this one's infinitely large, the bigger one is also going to be infinitely large. Okay, so that's kind of the idea behind the comparison test. So we can't use convergence to prove divergence, and we can't use divergence to prove convergence. Okay, because if I tell you, this series is divergent, it grows infinitely large, and this other one is smaller than it, well, that doesn't tell me if it converges or not. It just might be a little bit smaller, but still infinitely large. Or it could be small enough that it converges, but that's not conclusive. We can only be conclusive in these two cases here. So if one is convergent and the other is smaller, the smaller one is also convergent. And if we have one that's divergent and the other one is bigger, then the other one is also divergent. Okay? So in order to use the comparison test, we have to have a known series to compare against. So usually for our purposes, we're going to use the ones that we've talked about. These are kind of the more common ones that we work with. So a p-series, in case you've forgotten from just the last section, a p-series converges if p is greater than 1 and diverges if p is less than or equal to 1. And a geometric series, so that is going to converge if the absolute value of r is less than 1 and diverges if the absolute value of r is greater than or equal to 1. Okay, so those are two common types of series that we've looked at. Alright, so let's look at this first example here. So determine whether the given series converges or diverges. Alright, so when we're trying to find a function to compare this against, oftentimes we want to look at leading terms. So we're looking for leading term for large n. So when n is really large, what's the term that's going to dictate the behavior of this function the most? And in this case, it's going to be this 2n squared down here. So that one's going to have the most weight, the most pull on what the value of the function is. So we're going to use that as kind of our baseline to determine convergence or divergence. So we're going to compare. So our function 5 over 2n squared plus 4n plus 3 with the function 5 over just 2n squared. Okay, so the question now is ours bigger? Is it smaller? Or are they equal somehow? That's what we're trying to compare against. So notice the relationship between these two. So the denominator here, because n is going from 1 to infinity up here, n will always be positive. So we're taking 2n squared and adding a positive number to it. Whereas on this side, we're only taking the 2n squared. So for all values of n, greater than or equal to 1, this one is going to be bigger than this one. Okay, does everybody see that? So because we're adding more positive terms to it, the left one, our given series, is going to be bigger than the one on the right. Oh, did I say that backwards? Oops. Let me rephrase that. So this denominator is bigger than this denominator. Whew, yeah, that was almost bad. So this denominator is bigger than this denominator, but if the denominator is bigger, that means the entire fraction is smaller. Okay, so I kind of said that backwards. There we go. So this is actually going to be less than. Sorry about that. So again, just to summarize why it's less than, this denominator is bigger than this one for all positive values of n, so the fraction must be smaller than that one for all values of n greater than 1. Okay, so this is since the left-hand side denominator is larger. Okay. So then let's look at what we know. So if we're looking at the sum n going from 1 to infinity of 5 over 2n squared, we can go ahead and pull out the 5 halves, right? That's just a constant multiple of 1 over n squared. So we know something about this result. Can anybody think, hopefully, about either the convergence or divergence of that series? Hopefully the first thing you think of is it's convergent, and the reason why, because it's a p-series, and it's a p-series with p being greater than 1, right? P is 2. So let me just put that right here. So we know this is convergent because it's a constant multiple of a p-series with p equals 2, which of course is greater than 1. Okay, so we know that this series here is convergent because it's a p-series with p equals 2. So, therefore, since we know that this series is bigger than the one in the problem, and it converges, therefore our smaller series must also converge as well. Okay, so therefore, so the sum, and going from 1 to infinity, of 5 over 2n squared plus 4n plus 3 is convergent by the comparison test. Okay, so again, that argument of our series is smaller than this one, and I know that this one goes to a finite value. Therefore, our smaller one must also go to a finite value. So ours also converges. This makes no claim on what that value is, but that's not really what we're looking at right now. So, all right, let's look at another one. So test the series of ln of k over k for convergence or divergence. So let's look at what's going on here. So we've actually seen this one right in the last section. So notice that ln of k is going to be greater than 1 for k being greater than 3. Okay, now why are we saying for k greater than 3? Well, that actually comes from when we worked with this example previously. We saw that ln of x was greater than 1 for x greater than e, but we're only dealing with whole numbers here. So we can just mention this is since 3 is greater than e. Okay. So since ln of k is greater than 1, for k being greater than 3, we can say that ln of k over k must be greater than 1 over k for k being greater than or equal to 3. Okay. So again, we took that and just divided both sides by k. Oh, sorry. I was wondering why that wasn't matching up. This one should also be equal to. There we go. Okay. So now, let's talk about how this series would compare to this one. So the series 1 over k. So we know the series 1 over k is divergent. Sorry. I think that's going to happen a lot. Did you hear my Siri going on? Because I keep saying series and my phone thinks that I'm talking to it. Okay, so hopefully all your phones aren't going off listening to this. So we know that 1 over k is divergent because it is a p-series, and it has a p-value that is 1. So this is p-series with p equals 1. And this one actually was a special one we talked about. This is the harmonic series. So the harmonic series is divergent. Okay, so, but that's, we know that this series, so here comes the argument right here. This series is divergent. And our series is bigger, which means that it must also be divergent. Okay, by the comparison the comparison test. So we can say, thus, the sum, and going from 1 to infinity, of ln of k over k is divergent by the comparison test. Okay. So let's look at one more theorem that we have here, one more test for this section. So we have the comparison test, the two parts of that. Now we also have something called the limit comparison test. So the limit comparison test says, suppose that a and b are series with positive terms. If the limit of their quotient, so the limit as n approaches infinity of a over b, if that equals c, where c is a finite number and c is positive, okay, greater than 0, then either both series converge or both diverge. Okay, so this is going to be helpful when looking at two series side by side because we can just take a limit of their quotient, and then this doesn't tell us whether they converge or diverge, but it tells us that they will both do the same thing. So either both converge or both diverge. And so then if we can determine convergence or divergence of one of them, that automatically tells us what happens with the other one. Okay. Now this one, we actually are going to get a chance to prove this right now. We're not doing a lot of these proofs of these theorems, they're all in the book of these tests, but this one's a little bit shorter, and I think it's good to at least see one proof of one of these tests. So for this proof, we're going to start off here. So I'll do this. This is a different color. So we're going to let little m and big M be positive numbers such that little m is less than c, which is less than big M. Okay, so we're getting two values, one of which is smaller than the limit, one of which is larger than the limit. Okay, so because, and I'm gonna need some space. So because that quotient an over bn because that quotient is close to c for large n. So think about that. If the limit is c, then that means as n gets larger and larger and larger, right, we get further out towards infinity, that quotient is getting closer and closer to c. That's what it means to have a limit, right? So because this is getting close to c for large values of n, there is an integer. We're going to call it, there's an integer, we're going to call it big N, such that little m is less than an over bn, which is less than big M, when little n is bigger than big N. Okay? So think about that for a second. What we're saying is, eventually, so as we're heading out further and further towards infinity, this quotient, whatever it is going to get so close to c. So if we say that, this is the value of c right here, eventually they're going to get so close that they will be within this range, within the values of little m and big M, right? If we say little m is right here and big M is right here, right? Eventually, as we get closer and closer to c, at some point we will be within this range here in question, right? As we get further and further out towards infinity. That's what this is saying. Okay, so for large enough values of n, so further along the series, we will get eventually close enough that we're within this region of little m and big M. Okay, so what this tells us, if I go ahead and multiply b sub n to all sides of this, that gives us m times b sub n is less than a sub n, which is less than big M times b sub n, when little n is bigger than big N. So again, that's just saying as we go further and further out towards infinity. So, what is this telling us? Well, this tells us if the series b sub n I can get this in here. Okay, if b sub n converges, so does the series big M times b sub n. So think about that for a second. So if this series converges, multiplying it by a number, m, is not going to change that. right? If it converges to 5, then and m is, 6, then it's just going to converge to 5 times 6, which is 30. Multiplying by a constant is not going to turn a convergent series into a divergent one. So that's pretty much it. So since this converges when B converges, and this is bigger than this, so think about that, by the comparison test, if this one converges and it's bigger than this, our smaller one must also converge. Okay, so thus, our series A converges by the comparison test. Okay. There we go. All right, so again, follow that line of reasoning. So if B converges, MB converges. If MB converges, A converges because it's smaller than MB. Okay, so if you cut out the middleman of MB, we say if B converges, then A converges. All right, so that gives us the one case, and then the other case is going to be nearly identical to this. So essentially, I'm just going to fill in the gaps in a second. If B diverges, so does the series with little m times b. So if B diverges, so does little m times b. Okay. So then we can say that A also diverges by the comparison test. Okay. So again, if B diverges, then little m times b diverges, right? Because multiplying a constant by that series isn't going to somehow make it not divergent anymore. And if this diverges and our series A is bigger than it, it must also diverge. So if B diverges, so does A. Okay, that's what that argument is saying. All right, and then that's the end of our proof. So just draw a little box there. That just signifies we've finished the proof. So that's the proof of the limit comparison theorem, or limit comparison test, using the comparison test. Okay, so this allows us to now use an additional test to determine convergence or divergence based on series that we already know. So let's look at a couple examples using this test. So test the series of 1 over 2 to the n minus 1 for convergence or divergence. Okay, so of course the part we're talking about right now. So let's use the limit comparison test. With the following values. So let's pick a sub n to be our series, so 1 over 2 to the n minus 1, and then b sub n will be 1 over 2 to the n. Okay, and then let's take the limit. So limit as n approaches infinity of an over bn, that is limit as n goes to infinity of 1 over 2 to the n minus 1 over 1 over 2 to the n. Do some multiplication by the reciprocal there. We get the limit of 2 to the n over 2 to the n minus 1. Go ahead and multiply by 1 over 2 to the n to the top and bottom, right? Just again, our algebraic tricks for working with limits. So this becomes the limit as n approaches infinity of 1 over 1 minus 1 over 2 to the n. As n goes to infinity, this term, 1 over 2 to the n, goes to 0, right? Because its denominator gets really big, so the fraction gets really small, which means we're left with 1 over 1, which is just 1, which is greater than 0. Okay, so now, again, the limit comparison test does not tell us whether the series is convergent or divergent. It just tells us that they are the same. Either they both converge or they both diverge. But that value of 1 does not give us any other indication about, the 1 doesn't mean anything for what we're looking at. Okay, the 1 doesn't say, oh, it converges to 1. That is not what it says. It just says that either they both converge or they both diverge. Okay, so that's all this limit comparison test tells us. Okay, so the limit exists. So the limit exists, and the series 1 over 2 to the n is a series that we can actually find. So this is a convergent geometric series. Okay. So since the limit comparison test told us that they either both converge or both diverge, and we know, because it's a geometric series, that this one converges, therefore ours must converge as well. So therefore, the sum n going from 1 to infinity of 1 over 2 to the n minus 1 converges by the limit comparison test. All right. And then let's look at one more. So determine whether this series converges or diverges. So in this case, so let's use the leading terms of the numerator and denominator. Okay, to help us identify another series that we can use. So our series A is going to be just whatever we have here. So that's 2n squared plus 3n over the square root of 5 plus n to the 5th. So our series B, so the leading term in the numerator, that's 2n squared. And in the denominator, it would be n to the 5th, but don't forget it's in the square root here. So that's actually n to the 5/2 power. Okay, because I want to use the most dominant power in the numerator and denominator to help dictate its behavior. So this we can simplify a bit because we have n squared over n to the 5/2. So this is 2 over n to the 1/2. So 2 over root n. So that's going to be our series B. So generally this is a good policy of using that leading term, right, that highest power. But every problem is different. So sometimes picking b sub n, you're really just trying to pick something that we can actually know something about. So typically that's a p series or a geometric series, but anything that we know about is what we want to use. So let's take, the limit as n approaches infinity of a over b. So this is going to be the limit as n approaches infinity. So instead of writing these complex fractions, I'm going to put, 2n squared plus 3n over square root of 5 plus n to the 5th. I'm going to go ahead and just multiply by the denominator, by the reciprocal of that second one. So instead of putting it over the whole thing, I'm just going to multiply by its reciprocal. So n to the 1/2 over 2 instead. Okay. So then we get limit as n approaches infinity. So let's multiply that in. So the n to the 1/2 power, that's going to give us 2n to the 5/2 plus 3n to the 3/2 over 2 times the square root of 5 plus n to the 5th. Okay. Multiply by the highest power in the numerator and denominator, so that's 1 over n to the 5/2 over 1 over n to the 5/2. Oops. So this is going to give us 2 plus 3 over n over 2 times the square root of 5 over n to the 5th, because when you bring it inside the root, it changes the power. So that's going to be that plus 1. Okay. And then this, as n goes to infinity, that goes to 0, that goes to 0. So we're left with 2 plus 0 over 2 times the square root of 0 plus 1. So 2 over 2, which is 1. So again, that does not indicate convergence or divergence, it just tells us that they're the same. So since, let me separate this off here. So since our series B, so this is 2 times the series 1 over n to the 1/2. Hopefully you recognize what type of series that is. It's a p series. So this is p series with p equal to 1/2, which is less than 1. So this series is divergent. So since that one is divergent, our given series must also be divergent. So the series from 1 to infinity of 2n squared plus 3n over the square root of 5 plus n to the 5th diverges by the limit comparison test. There we go. All right. And that's our last example for section 11.4. So when we come back next time, we're just going to keep continuing on talking about these infinite series and how we can test them for convergence and